Ok, bienvenidos al coloquio Arcadio Poveda. Me voy a alejar de Aldo, está reverberando esto.
Empezamos. Con el volumen es el que hace el eco de la máquina. Eso. A ver ahora.
Hola, se oye mejor, ¿verdad?
Eso es de ella.
Es de don Abraham. Bueno, buenas tardes a todos, bienvenidos. El día de hoy tenemos como ponente al doctor Aldo Rodríguez Puebla. El doctor Aldo hizo sus estudios de licenciatura en la Escuela Superior de Física y Matemáticas del Instituto Politécnico Nacional. Posteriormente realizó sus estudios de maestría y doctorado aquí en el Instituto de Astronomía de la UNAM. Su tesis doctoral, bueno, él se graduó con honores y recibió la medalla Alfonso Caso por su tesis, que fue la mejor tesis en ciencias, con título La conexión galaxia-halo y su evolución. Posteriormente realizó una estancia postdoctoral de 1 año en la Universidad de Shanghái, Jiaotong, en China, y una estancia de 2 años en la Universidad de California en Santa Cruz, en Estados Unidos. Desde 2016 forma parte de la planta de investigadores del Instituto de Astronomía de la UNAM. Actualmente es investigador titular B y miembro del SNI nivel 2. Le agradecemos mucho que haya aceptado darnos este coloquio el día de hoy. El título es The Coevolution Between Dark Matter, Halos and Galaxies. Adelante.
Ok, ¿se escucha a buen nivel? Sí, ok, qué bueno. Bueno, hay gente que no habla español en el auditorio, así que voy a cambiar a inglés. Well, as you see here, by my title, I'm still doing what I was doing at my PhD. So this is actually part of the ideas that we had when I was doing my PhD. So most of this work has been with a collaboration of a large group of people, well, a middle large group of people. So here with the people that I was doing my postdoctoral research at GCSE, and here with the local people at UNAM. And sorry about this, is Miguel Enriquez, my other postdoc. So Daniel Salazar, who is over there, it's our PhD student. Rubén Calet, who is there, is our postdoc, and also Miguel Enriquez, who is our postdoc. Okay, so this talk will be an interface between observations and simulations. And however, most of the time, in the way that we study galaxy evolution, we do it essentially in 2 ways. So we have one empirical approach, which is normally we call it empirical modeling. This is an approach that is observational motivated. So essentially we have, for example, the spectra of the galaxies. We can perform things like fossil record analysis like Sebastián Sanchez is doing. Also, we can use the galaxy population, in which we can, based on the galaxy stellar mass function, we can infer how galaxies are growing. And by combining with a specific star formation rate or the star formation rate versus the stellar mass. The star formation rate is the amount of stars that galaxies are creating in a given time. We can study how galaxies evolve. And essentially, these two tell us in a very simple and empirical way how galaxies should be evolved. The problem with this approach is that it doesn't tell anything about the cosmological context of those galaxies. So for example, the fossil record doesn't tell you anything about how the mergers are happening within these galaxies, which fraction is in situ or which fraction is ex situ. And the galaxy population model, it's hard because you don't know how galaxies are evolving through the galaxy stellar mass function. Although we have a recent paper that you can check and we tell you how to do that. In any case, there is the other approach, which is the theoretical approach, where you want to start from the basic equations, put them in some kind of machine, then run everything to get how galaxies form and evolve. So in the theoretical approach, you start by assuming some structural formation model. In our case, it will be the lambda CDM, because it's the most successful structural formation model. And we have two ways to do this. So either we analyze hydro simulations, or we can use semi-analytic models. In the case of semi-analytic models, what you are expected to do is to use phenomenological rules that summarize the whole physics that is happening in galaxies. This is failing, right? Or el micrófono parece que está fallando, ¿no? ¿O no? Como que, okay. Yeah, so the semi-analytic models use phenomenological rules in order to summarize the main mechanisms for galaxy formation and evolution. In hydro simulations, you are expected to put all the physics. However, we have issues with resolution in these simulations. And at some point, in order to be computable, feasible, we need to summarize the physics based on analytical models most of the time at the level of the formation of stars. In any case, these two models are computational very expensive. So there is a third approach that when I was a student, it was not so popular. And sometimes in some conference, people from here rejected this kind of models because they said that there was not physics in there. So this third approach, there is no physics in this, but it tries to take the best from the theoretical approach and the empirical approach. The idea here is to try to match the galaxy population with your structural formation model to infer empirically how galaxies form and evolve. Okay? So this talk will be about those models. So the idea or the goal is to build a model that is consistent with observation and a cosmological structure formation model. The idea is not introduce any astrophysics, but then do the reverse engineer and infer what is the astrophysics behind this connection. So this is very powerful, right? Because you are trying to be consistent with the observations and the cosmological structure formation model. So these two connections, it's what normally people call the galaxy halo connection. So we start with n-body simulation, for example, where we can know how dark matter halos are distributed with this simulation. We can perform things like the spatial clustering of these dark matter subhalos, count them. We can also infer their properties, their angular momentum, concentrations, masses. We can know everything at some detail in those simulations. And then we can ask the question, how these halos compare to the observations and match them. So this is my machinery that I'm going to talk about statistically. So there are different ways to perform this galaxy halo connection. The most direct, or what we believe is one of the most direct techniques, is to observe galaxies and the distortions around those galaxies through weak lensing. So based on these image distortions, we can measure the total dynamical mass that are creating those distortions. So we can estimate what is the dark matter halo of a galaxy that is surrounding that galaxy. We can also use satellite kinematics in a way that, imagine that you have a galaxy, for example, the Milky Way, and imagine that you have the large and small Magellanic Clouds, and you can use those two galaxies as test particles in order to measure what is the dark matter halo of the Milky Way. And actually, we do it here. So some people are using stars and also those satellites to measure the halo mass of the Milky Way. We can also use galaxy groups and clusters in order to infer the dark matter halos. So essentially, maybe you remember this story by Zwicky, where he was using the velocity dispersion, which is something very similar to satellite kinematics in order to measure the halo mass or the dynamical mass of those of their dark matter halos. Now, there is a no. Oops. Oh. There. I thought that there was another slide here, but it seems to not. So there is these three techniques that I described here are in some way direct techniques. Now, there is another whole world of techniques that are at a statistical level, which is what if you compare the galaxy clustering of the galaxies, and then you use n-body simulations to put galaxies within that n-body simulation, and then compare the resulting clustering. So you perform this in an iterative way until you match the observations. So people from the past, and I think here at IAUNAM, we were very pioneer in this kind of technique back with Pedro Colin. They perform clustering, then do this in iterative technique and how to put galaxies into dark matter halo simulations. And then you constrain things like the stellar to halo mass relation. So what is the halo mass as a function of your stellar mass, or luminosity to halo mass relation? And there is a second technique, which is easier, and we've been trying to master here in our group, which is the abundance matching approach, which is the thing that I'm going to talk about next. So what I'm showing here in the y-axis is the cumulative number density of dark matter halos and galaxies. So this x-axis is the mass. So this is the galaxy stellar mass function, the halo mass function, and their cumulative versions. What it's important to know about these two distributions, and if you were my student at the courses, you will know that these two distributions can be written in a form that they are probability distribution functions. So if you want to know how to project one probability distribution into other, the idea is to match their probabilities. And it makes sense, because if you want to understand what is the probability to observe a galaxy within a dark matter halo, it's better to be equal their probability, right? So this is what it's essentially telling you. So and the way that this works is that you pick a stellar mass, you look into the cumulative number density, and the galaxy stellar mass function, you then equate this number density with the cumulative halo mass function, and then check what is the halo mass. So you can put a point in this plane, which I'm plotting here the ratio between the stellar mass and halo mass as a function of halo mass. Then you can pick another galaxy, the stellar mass of a galaxy, and then do the same thing and look for the halo mass and put another point here. The idea is that you could do this in a continuous way, and you will have this very strange peak here. So the idea of this figure, and the idea to put this y-axis, the stellar mass over the halo mass ratio, is that it will tell us of what is the efficiency of that baryons were transformed into dark matter halos to create the stars. Okay, so
Very quick question.
Sure.
On this technique. So the basic assumption to make this length is the basic assumption to be sure of this length is that what mergers are halos, galaxies do not merge.
I will talk about that. Yes, this is the statistical level, and part of my talk will be on how to do this matching for individual halos and then individual galaxies. But yeah, I will come back to that point later. So, there are large groups trying to infer this ratio, which tells us the efficiency of star formation within dark matter halos. And let me show you one of the most recent results of this relation. So this is measured at redshift around 0.1, so it's the local universe. And you can see here different authors. All those authors have different techniques, have used different techniques. For example, those that I showed you of the direct techniques, for example, using galaxy groups, which is represented by this CSM-MF or CL, but they are using galaxy clustering, like for example, this, there is no galaxy clustering here. Well, really, it's apparently clustering. But the point here is that there are different techniques, and all those techniques are agreeing that we know that we know the shape of this function up to some degree. Now, focus on this shaded area. This shaded area, it's our systematic error in stellar masses. Okay? If you believe that we know stellar masses for local galaxies, you're wrong. So we have this area of systematic errors. So all those techniques are within the systematics, and we are happy with that. At least the people that we are doing this, we are happy with that. And we know that this function, that the shape of this function, there is some physics behind this. So at lower masses, we believe that because they have shallower potentials, the dark matter halos, reionization, stellar winds, and supernovae can prevent the formation of the stars and produce this very low star formation efficiency, even though those galaxies have higher star formation rates, okay? Specific star formation rates. On the other hand, we have that at higher masses, AGNs are producing this inefficiency for those galaxies, for those massive halos and galaxies. Now, take into account that galaxies that are in the center of these dark matter halos, which are most of the time zeros or elliptical galaxies, these dark matter halos are hosting clusters. So we are taking into account the whole dynamical mass of those groups, and maybe this is an apparent. Even though if you add all the stellar mass contained within the dark matter halo in those groups, it will flatten a bit, but it won't be sufficient to have higher star formation efficiencies around this peak. And the peak, do you know which galaxy is in the peak? Would you like to guess? The Milky Way. Well, the Milky Way is slightly at the left. It's already entering into this phase, but that's another story. Okay. Well, so if we use these stellar to halo mass relations, or the stellar to halo mass ratios, and we put them into n-body simulations, and what I want you to imagine is an n-body simulation with dark matter halos, and put galaxies over there, we can compute things like correlation functions. So what I'm showing here is the two-point correlation function in different stellar mass beams for the local universe. Observations are the circles, and the result from this simple technique of put galaxies into dark matter halos are these solid lines. So this is a paper by one of our students who has the coolest last name. His last name is Dragomir, and I always thought that it was the coolest last name in the world. So, here he's showing that if you do that with these very simple techniques, you can reproduce the clustering of the galaxies just by that simple technique. From the beginning in my PhD, we showed that using again this very simple technique, you can reproduce counts in galaxy clusters, which is the thing that I'm showing here. It's like performing mass functions of clusters, stacking them within some mass beam, and you can see that the counts, which are these symbols, and the predictions from this simple model of abundance matching is shown with this like violet region. So it's agreeing with that. And also, we can reproduce counts of fractions of satellites. So this is essentially an outproduct of reproducing clustering and counts on galaxy clusters. We've been beyond in our group, we've been trying to understand better these correlations in a way that we are asking ourselves. I haven't said anything about whether this relation is consistent between centrals and satellites. One of the things that we discovered in my PhD was that the relation between centrals and satellites are very different, and that indeed there is some astrophysics behind this difference. I'm not entering too much detail, just saying that you can do those assumptions, and then you can reproduce things like the clustering and actually measure the scatter around those two relations. Now, another thing that it was very surprising is that this simple technique, abundance matching, if you ask what is the dependence of the mass of the observed galaxies mass function with the environment, which is the thing that I'm showing here. So if you see this color like violet, it's essentially voids, and as we go to darker colors, we are going to cluster regimes. So the observations are the circles, and I'm plotting here the galaxy mass function. So if you ask the question, what if I use this simple technique of the subhalo abundance matching into n-body simulations, and I measure the environment of the galaxies in a similar way as I did in observations, then you can compare with the observations. So the shaded areas that you are seeing here, forget about the solid line, those are fits, but the shaded areas are the results from the simulation. So we haven't put anything about physics. We haven't put anything to just to tell to the halos. If you have this mass, the corresponding stellar mass or luminosity should be this according to subhalo abundance matching. When I've been trying to show you or convince you that this is apparently sufficient to reproduce observations. Now, for me, this is a very successful simple model that can tell you about how galaxies are populating the dark matter halos, and you should take that seriously. Another thing that is very important and more philosophical implications is that if this simple technique is telling you or reproducing the observations with this degree of accuracy, then there must be something real with the dark matter simulations, or dark matter, with the existence of dark matter. I think that was another slide that should be there. Okay. And we went beyond. Previously, I was showing only the environment of galaxies for all the galaxies. We then divided into centrals and satellites. And you can see, again, the symbols are observations. The shaded areas are the model by abundance matching. And you can see that in different types of environment that we are showing here, we are going from voids, field, clusters. We are reproducing the counts of galaxies. This is actually very amazing. Now here, Daniel is working in repeating this kind of work, and not with the idea to show the same thing, but the idea to test if we can understand better what is behind the driving force of the evolution of the galaxy's mass function with environment. So if you want to talk about that, talk to Daniel. Another question is that do all the galaxies have the same stellar to halo mass relation? As I said at the very beginning, this kind of simple techniques tells you that the stellar to halo mass relation is universal. Where you can actually ask the question if this stellar to halo mass relation is indeed universal. So here in this paper, we asked the question of what happened between quiescent and star-forming galaxies, central galaxies. So what we found, and what others have found also, but only through weak lensing, Here we did it by the combination of galaxy clusters and groups. We showed that the halo masses at a fixed stellar mass, the halo masses of star-forming galaxies are smaller than those of quiescent galaxies. And the idea, very simple idea that we thought it was nice to describe this, is that imagine that the stellar to halo mass relation does not evolve with redshift. So galaxies are evolving around this relation. And then at some point, they quench. Their galaxy stellar mass function does not evolve, but the halo mass grows gravitationally. So they are migrating in this way. So it was a very nice and simple way to explain this correlation. However, other people have asked the same question. And with essentially the same data that we use in our paper of 2015, others have tried to measure the difference between these two stellar to halo mass relations. Okay? So remember, at a fixed stellar mass, quiescent galaxies have larger dark matter halos. This means that those models, like mine, that produce larger halo masses for quiescent galaxies should be in this region. So look, for example, this paper by Moster, he's in the other way around. Papers like Universe Machine or Su and Mandelbaum, they are around this region, showing that there is no difference. So people essentially with the same data and with different assumptions are in tension within this inference of the stellar to halo mass relations for star-forming and quiescent galaxies. And this has very strong implications of how galaxies are populating dark matter halos, because those models that assume that there is no difference between star-forming and quiescent galaxies, there must be something extra to those halos to explain the observed clustering of galaxies. I'm not entering too much detail because it's a bit complex, but you can ask me later. And if you have an hour, we can discuss about that. But the idea is that those models that have equal stellar to halo mass relation, or even in an inverted way as us, they need a secondary halo property, which will produce something that we call halo assembly bias. This second property, most of the time, the formation time of dark matter halos, in the past, halos that formed earlier form in a universe that is much more denser, and then they are more clustered, okay? So in order to explain the clustering of those galaxies, they need to invoke these kind of mechanisms of halo assembly bias. On the other way around, models like mine, that is saying that quiescent galaxies live in higher mass halos, well, the idea is that higher mass halos are more clustered than lower mass halos, and then the halo mass is the key in this way, in this region, and it's the only explanation for the difference. So this was the work of our PhD student in Santa Cruz, and what we did is to take the specific star formation rate versus the stellar mass, divided in different chunks, as you are seeing here, and compute the clustering in all those regions that we are showing here. So bluer colors are galaxies with high star formation rates, and redder colors are galaxies with quiescent star formation rates. So what I'm going to show are clustering measurements in each of these chunks of the figure. So these are the results. So in the y-axis, I'm plotting the two-point correlation function, and this is the distance, and the different bins are different stellar masses. And the different rows are different star formation activities. So these two upper rows are referred to star forming main sequence. This middle row is for green valley galaxies, and this lower row is for quiescent galaxies. Observations are shown with the circles and error bars. And now, this is the interesting thing. We are computing correlation functions of central galaxies only. The dashed line, the black dashed line, it's a model in which if a dark matter halo is accreting a lot of material, then you are supposed to assume that the galaxy, it has a higher star formation rate. The blue dashed line, it's a similar model in which halos are very concentrated. We are expected to host elliptical galaxies, for example, very dense galaxies with low star formation rate. So these two models are referred to this secondary property of dark matter halos, halo assembly bias. And the halo model, which is shown with the red line, is the one that has a segregation in the stellar to halo mass relations. So to our surprise, there is no difference between these models. So that's why people using the same data, but with different assumptions, we're getting different answers. So we thought we should be much more smarter than that. So what we thought is to perform cross correlations between galaxies. So what we did is to take central galaxies in these different regions and correlate with satellite galaxies for the same mass, okay? So for example, we took central galaxies here, we cross-correlate with all the satellites at this stellar mass in order to get some clustering. So, and these are the results. So again, these two models, if you focus on in blue and black, these are halo assembly bias models. In red, it's my halo model, okay? And I was expecting that my halo model will win this battle. And indeed, check out this. So, for example, here there is a very strong difference. Here as well, here it's hard to tell. But essentially what our model what our experiments told us is that the clustering in these galaxies is driven by the halo mass, not by the halo assembly bias. And this has very strong implications for in the way that we are. In the simulations, because then you will run away very quickly with the halos that were populating those galaxies. That was just the explanation. So essentially, with the analysis that we did, we conclude that here I'm plotting again the halo mass versus the stellar mass, and this is like the new version of the plot that I made already like 10 years ago. That a fixed stellar mass, star-forming galaxies have lower masses than quiescent galaxies. So we have confirmed that this is the best way to obtain this model. We've been also studying the connection with H1 gas mass. So here Ben has been doing this fantastic work. He's been analyzing very small samples of galaxies containing information of H1, H2, morphologies, and stellar masses. So you can imagine that he's working essentially with hundreds of galaxies and trying to infer the PDFs of those galaxies. I'm not entering too much detail because I think Ruben should give a colloquium in the future and talk about that. But our main goal to do this was to understand how H1 gas mass was related to dark matter halos. So in the upper row, you are seeing the stellar versus halo mass. Just focus on the panels on the left. You're right, my left. So focus on this relation. So the stellar to halo mass relation, as I said, is a very tight relation. It has a scatter below 0.2. But for H1 masses, it's a very complicated distribution. So you can see here that it seems apparently bimodal. As you go to higher masses, essentially there is no correlation with dark matter halos. And then the question is, our hydro simulations are obtaining this kind of relations because this was very empirical. At least we showed that, again, because the clustering is very powerful in this case, we showed that the clustering is reproduced, and you should focus on the here, I guess that is this dotted line that is just slightly above of the violet line. So our model is reproducing the clustering and H1. And the idea here is that we are comparing with alfalfa, and there are a lot of selection effects in alfalfa. So we also try to mock up all those selection effects. But the real clustering that you should observe in galaxies is the red curve. So, for example, the fact that we are seeing that there is a deficiency of clustering at these masses is because the selection effects of alfalfa, but the real clustering is this one. So we are now trying to understand what is the selection function of alfalfa. Okay, but this was everything at redshift 0. What we are trying to do, it was just to play this game of matching dark matter halos with galaxies. But now, what I want to show is this new semi-empirical modeling that I'm developing, which I'm calling the next generation of semi-empirical modeling. And the best that I could come up with this with these words was empire, which I think sounds catchy, but sometimes when I present this, and especially in US, they are not very happy with the title. But in any case, everybody knows that what it's empire. We did with that before. Okay, so the idea of empire is to use the power, the best of the best. So in embodied dark matter simulations, we can know with a lot of detail the dark matter halo properties that we simulate in these very large cosmological simulations, and we can know what is the history of those dark matter halos. So what I'm going to show here are the results by combining these two simulations, although we are working in a new, with new simulations, but the results that I'm going to show are based on these simulations. So just look at this. This is the merger tree of a dark matter halo of this mass, 8 times 10 to the 12, of redshift 0. And you can see how chaotic is the history of this dark matter halo, all the mergers that it has. On the other hand, we have this halo of 10 to the 11, and it has a very quiet formation history. So this must have some implication for the galaxies that are inside of those dark matter halos. So the idea is that we will transform those merger trees into galaxy merger trees. And moreover, we will differentiate between star-forming and quiescent galaxies. And we will have a lot of properties for those galaxies in order to be consistent with a huge battery of observations. So essentially how this works, so we will read this, this figure clockwise. We will start with this panel. So what you're seeing here is the maximum circular velocity of a dark matter halo. This is the most massive one of those simulations as a function of redshift. So you are seeing here how the halo is evolving, increasing in their maximum circular velocity. And then the idea, because this is a monotonic increasing function, the idea is that this quantity will work as a clock to the galaxies to tell how they should evolve, right? So this is what I'm going to do here. By the way, there are here numbers, some specific epochs for the galaxy that will be connected with the, sorry, for the dark matter halo that will be connected with the galaxy. So, so then we can use now individual stellar to halo mass relations for our galaxies. We can parameterize that. And we can obtain how the galaxies are evolving within this kind of Tully-Fisher relation, which is the stellar mass on the y-axis and the maximum circular velocity on the x-axis. So where time is increasing in this direction, remember that we are saying that time here is essentially time here. So this is increasing in Bmax and also increasing in the stellar mass. And then we can project this into the evolution of your galaxy. Now let's interchange Bmax with the redshift. So you have here the whole history of your galaxy. Now imagine that you take a point here and then you take a point nearby and you take the difference and divide by the time that took that difference. Well, that's the star formation rate of your galaxy. And because we have all those mergers, we can measure how much of the mass will form in situ and also ex situ. But also there is something very funny that we discovered in one of our previous papers, that you can measure the intra-halo mass either by collisions between satellites or stars that expel into the intra-halo mass distribution, okay? So this is what a merger tree in Empire looks like. So what I'm showing here, this is the main progenitor, and this is one of the most massive galaxies, which I expect is an elliptical galaxy. And you can see all the stuff that is merging with this galaxy. The color code here is the specific star formation rate. So there is a lot of going on here. And this is just the halos that merge into the galaxy. I'm not plotting the subhalos. This will be a very crazy plot. This is, for example, for star-forming main sequence galaxies. You can see that it has, no, sorry, this is for a Green Valley galaxy. So you can see that it is not as mature as the elliptical galaxy, but the history is slightly more quiet. Okay, so I brought some movies, very archaic movies, so you can see how in a 20 megaparsec box, how these galaxies are evolving and merging between each other here. So you can, the size of the circles are proportional to the very radius of those halos. And we are going from very early in the universe to up to redshift 0. You can see here how mature. Right. These are only galaxies. Right. So you can see here everything is a star-forming main sequence with a lot of higher star formation. In the nodes we have quiescent galaxies, which are expected to be elliptical galaxies or something like that, or cluster, right? And here is the formation of the most massive galaxy in the simulation. So you see all those galaxies are merging with that galaxy, and then this is like the dusty star formation phase, and you can see how they interact. It is happening very fast, but at the end, only one galaxy survives that. It's around this part here. Okay. So what we are doing? Well, essentially we are reading all this information from the simulations, and we are proposing that galaxies have different properties and that we will match all those properties to the merger trees of the dark matter halos and their properties. So this is our part of the theory. This is the connection of the rules that we will say that galaxies should follow, and then we will fit to a lot of observations. Observations are here. So we can go from this dark matter embodied simulation and then reproduce the observable universe. And all of this is based on a Bayesian fit in order to have robust measurements. And well, if you are interested in our observational constraints, so here I'm showing the galaxy stellar mass function from redshift 0 to redshift 9, the fraction of central galaxies, redshift 0.1, quiescent galaxies, the mass function of quiescent galaxies up to redshift 4. The new ones that we have go to redshift 5, which now observations from the James Webb allow to do that. The star forming main sequence, the cosmic star formation rate, the infrared luminosity function. Here I'm showing the ultraviolet luminosity function because we have information about dust, and this was very influential from with the collaboration from with Itziar Restaga and I just forgot his name. And Araceli Nava. So we are also trying to reproduce sizes of the galaxies. So here we are plotting the half-light radius as a function of the stellar mass. We have a model, a motivated model, which I'm not going to describe here, but you can talk to me.
You said that this is a compilation of tens of observational papers.
Right. Yeah. The work here is tremendous. All the homogenization, the compilation, understand what they are measuring, all that. It takes years. I don't recommend to do this kind of work, but because it takes years to do that. Also, we have quasar luminosity functions. So this is something interesting in the model. So we have two types of supermassive black holes. We have supermassive black holes that are active, which can be related to quasars or AGNs, and also to radio AGNs. If you want to know more about that. So if you want to know more about this model of supermassive black holes, you can go and talk to me as well. The idea is that we want to use this information to understand how galaxies are quenched by these two modes of AGN. And let me show you some preliminary results. So what I'm showing here are the stellar to halo mass relations compared to previous models. So essentially we are recovering what previous models are claiming. By the way, there is no tension with the lambda CDM because that was something very horrible that they did in the paper by the James Webb, but we are not getting tensions with the lambda CDM. They are consistent with previous models. We are reproducing that at a fixed halo mass, essentially for most massive galaxies, that a fixed halo mass, stellar mass, the dark matter halos of star-forming galaxies are smaller compared to large galaxies. We are recovering the clustering, the same figures that I showed before. And this is our main plot. This is our money plot. So, do I have 5 minutes more to discuss this? Okay. So, what I'm showing here is the stellar mass, and then this is the redshift, okay? The color code tells the star formation rate of the galaxy. So, let's take this white track that is here. So, what I'm doing here is to stack a lot of dark matter halos, well, galaxies from the simulation to produce a stacked track history of galaxies that will be represented by this galaxy that is here. So this is a galaxy with a final mass of 4 times 10 to the 11. So we see that around redshift 2, this is 1 plus e. So our redshift 2, it doesn't increase too much in mass, right? But has a very rapid phase here, okay? And you can read off this as well from this axis, where is the star formation history. So you can read that at redshift around 7 and 8, it has around a few solar masses per year. Then when it goes to redshift 2 and 3, it has hundreds of solar masses per year. And then when it enters around this region, there is no more star formation, okay? There is very little star formation. And you can read the same thing for all these white lines. You should infer here that there are a lot of white lines for a lot of halos here, but these are the main stuff, okay? Now, this dashed line is the observations of what is when the fraction of star-forming galaxies is equal to the fraction of quiescent galaxies, that is 0.5, okay? So essentially, this galaxy quench in the correct region where it starts to decrease very quickly in their star formation history. We are also putting this number here, which some people say that is a very good number to define quiescent and star-forming galaxies. So this plot is telling you this region, galaxies that were quenched at redshift 0, it's because they start to decrease the star formation rate on this region. Galaxies that are below that region are more statistically star forming. This is a statistical information. However, we have the information for all the halos in the simulations. Now let's look into another quantity, the infrared luminosity. So redder colors are dustier galaxies, which is this region, which was again the region of large amounts of star formation. So this means that the dusty star formation region, it's around here for these masses in galaxies and at these redshifts. And it's very consistent with what we know. And of course, this is motivated by the observations, okay? And also supermassive black holes. So this is a bit surprising, this figure here. So we are showing the ratio between black holes and the stellar masses. So we are going from 10 to the minus 4, 10 to the minus 2, which is the mean relation of local elliptical galaxies. And that's why you see here redder colors. But it seems that there is no dependence with the track, but rather is the dependence with galaxy mass, right? So we need to still investigate about that. And I will stop here and show you a summary and conclusions.
Thank you, Aldo. ¿Tenemos tiempo para preguntas? Questions?
Los dejé fritos, ¿verdad?
Chucho.
Yeah, your last 3 ones are really wonderful. Can you go back to the first one, whatever, the one with star formation rate?
This one?
Well, something that is, I mean, this is very useful. And one thing that is very interesting is that the properties at redshift 0 between the bright, let's call ellipticals and quiescents, and the dwarfs is really a bimodal thing at redshift 0. So that observation that can be really very precise with current surveys is one way in which you can really collaborate around your predictions. But very, very, very beautiful.
Right. So imagine the star formation rate versus mass. So we have a plot that looks like the local universe, and you can ask questions of a fixed mass, highly star-forming galaxies, where they were in the past. Were they very highly star-forming all the time? They were below the star-forming sequence. You can ask those questions. And I think Sebastian Blanc, the guy over there, he asked those questions during his bachelor thesis. But yeah, and he will ask again those questions.
Do you find a tight correlation between LR and the star forming rate?
Right, yeah. So
Because I don't know, I saw that you showed the diagram very quickly.
yeah, so we can do this. Let me do this. This is far infrared here. Now I will go to star formation. It's broader. But yeah, But yeah, you can define here. So you can now define, for example, the region of dominance of the dusty star-forming galaxies, and I think redshift 7, 8, we should find some dusty star-forming galaxies. Aditya.
Yeah. So my question is specifically for the massive galaxies. So we know that massive galaxies have a lot of contribution from mergers in the growth of their stellar mass, and that is also related to how they quench. So I was thinking in that plot, the curve that you show for the massive galaxies, is it actually all in situ star formation, or it's like a combination of both in situ and ex situ, which is in that SFR?
Yeah. So here is in situ formation. So that is whatever is in the ISM, it collapse from a molecular cloud and form stars. This is this quantity. Of course, I'm not modeling that, but I'm checking that from observations. But if you see here, right. So when we approach this region where it's decreasing very fast in the star formation history, this region that is zero star formation rate, and I can tell you that these galaxies have zero star formation rate. You see that the mass, that the track here for the mass is increasing, but this is due to, right, this is due to mergers.
Okay. Thanks.
Dry mergers.
I just want to comment about the field luminosity. In the paper with Araceli Nava and Itziar and we were able to, for this kind of results, to show that the luminosity, field luminosity, FIR, luminosity function, the counts,
Cosmic star formation.
in 1 millimeter, 1.2, and 2 millimeters agree very well with the observations. Yeah. So
Yeah, so this is very consistent. And I didn't put a slide from what is coming with this model in the future, but you should be aware that we are putting a lot of things. So, for example, because we have the star formation history in the dust in these galaxies, we can now run stellar population synthesis models over our tracks and put luminosities. So we will have a spectra for those galaxies. This is something that we expect that a postdoc will do in the near future. We are also working with Ruben and Daniel over there in trying to understand the history of the gas. So according to the mass, the stellar mass of the galaxy, the star formation rate, their colors, we will put the gas. And we will be able to make a similar plot like here, but with gas mass, H1 and H2. But also, another thing that will be very interesting to to do is that with these simulations, we can project in any type of observable that you might want. We can do light cones. So if you have an idea to produce a galaxy survey, you can ask us and tell us, well, I'm planning this kind of survey, and we can observe your galaxies and make predictions about what you are planning to do with your galaxy survey. Actually, in Toltec, they are doing simulations with a very preliminary version of this model. So all those simulations that they are doing with Toltec, they are doing with a preliminary version of this model. So anyone interested in do that, it's welcome to join. And the last thing, I think Daniel over there will also help to put dynamics to the galaxies are here. So they are not longer points, they will be spatially resolved galaxies. Any resolution that you might want, because we can put any number that we want. Yeah. Well, if your computer can store that information, that's fine. Okay. Mm-hmm.
Just a quick question regarding the AGNs, of course. Have you tried to use the accretion rate normalized to the black hole mass in order to see if there is a tendency?
Right. Yeah, I see what you mean. Yes, because I'm more in the galaxy evolution part. So what we are doing is this like a specific halo accretion, black hole accretion rate versus a specific star formation rate. So what we are seeing is that when galaxies, when we have AGNs, because we have the two modes, the AGN mode, quasar, for us is the same thing. One is brighter and the other is not. But we have also the radio AGNs. So we are doing those plots for this kind of quasars AGNs versus the specific star formation rate, and we are seeing some correlations. For us, it's like a time scale of quenching, like a diagnostic.
No more questions? Can you show us again the last coevolution of the supermassive black hole?
Ah, sure.
Because I think I missed something. Mm-hmm. So how do you explain this behavior in the high redshift region?
Right. So this region is of low. So what I'm plotting here is the black hole mass to stellar mass relation ratio, and so what you are supposed to read this figure is that, again, this is the track for this galaxy, ended up with this ratio. So in the past, it has this ratio on average. So it means that at higher redshifts had very low ratios of 10 to the minus 4. So it was increasing. The black hole mass, of course, is also increasing in mass, but the galaxy is increasing much faster compared to this dark matter.
It's more clear for me, thank you.
Mm-hmm. Essentially for all masses, yes, because right, yeah. So by the way, Alan over there, he made an extreme value statistics analysis of these very supermassive black holes, and we found that the observations that I'm using here will be consistent with those observations. So there is no tension in this part.
Okay, let's thank our speaker again. Thank you, Aldo. So I am going to do an announcement. Next week, we will have 2 colloquia on Wednesday and Thursday, so be prepared, please. We have an invited guest on Thursday at 12. A las 12, 2 coloquios, miércoles y jueves. Gracias. It's a surprise. Italian guy.